Now let's talk about rate of change. Let's, again, scroll past the formula to set it up a bit. So let's start with average rate of change. So that means change in well, whatever is changing over the amount of time it takes to change. So we looked at a more specific average rate of change, velocity and slope in previous problems. Average rate of change can apply to anything. So let's consider a function y equals f of x, which represents some quantity that changes over time. So then the average rate of change would be the change in y over the change in time. So if time is measured as x, then it would just be change in y over change in x. So this value corresponds to the slope of a secant line between these 2 points, where x is our times, so x1 and x2 are 2 different times, and f of x1 is the amount of that quantity at time x1, and f of x2 is the amount of that quantity at time x2. The instantaneous rate of change, going from average to instantaneous, similar to what we saw with any curve and our velocity functions, is just taking the limit. So if this is the rate of change in general over some amount of time, the average rate of change, then we take the limit of that, and then we get the instantaneous rate of change. So here's our average rate of change, and I just make that time, the denominator, 0, and as I get closer and closer to 0, I find the instantaneous rate of change. So all I do is take the limit of the average. So this value represents the derivative of a function at the point, our starting point, because we're trying to make x2 closer and closer to x1. So hang on. So here we have our limit as change in x is going to 0. So if we're using this function, this traditional slope function, change in y over change in x, we're having x1 is getting closer and closer to x2. So actually x2 is approaching x1 because x1 is our stationary spot, and we're getting closer and closer to x2. Or if we think of that time change as h, then our x1 we could really just call a, that's our initial time, or t, let's use t for time. So we'll call it t naught. And then our second point could be, we could think of it as t naught plus h. So that then we could write this limit as the limit taking h to 0. So this distance between the first time and the second time is getting smaller and smaller. So our change in time, or change in x, is now just h, and our change in position, I'm sorry, not velocity, but our change in quantity, whatever y is representing, is going to be the difference between this f is now, let's see, for our point Q is now t naught plus h. So our f of that is, our y value is the f of that input. And our p point is t naught f of t naught. So our limit is going to be f of t naught plus h minus f of t naught, where h is getting smaller and smaller, and our quantity, so our quantity is changing from this distance right here, would be the numerator, would be f of t naught plus h minus f of t naught, and that thing I'll do in green. So that numerator is representing the change in y, and the denominator is representing h, or the change in x, or time. All right, let's look at what this means. So an example of rate of change problem will look like this. A number of bacteria after t hours in a controlled laboratory experiment is n equal to f of t. So what is the meaning of the derivative f prime of 5? And what are the units? So our function here, n equal to f of t, that means time. T is our input. That's time. It's in hours. And the n is the number of bacteria. So that's our output. So the n equals the number of bacteria t hours after the beginning of the experiment. And then the second part of the question is, okay, so what's the derivative mean? Well, the derivative is the rate of change. So, well, let's talk generally first what the derivative means. That is the rate of change. How much has the bacteria changed over time t? And so it's really an average, the average rate from 0 to t. The rate of change of the bacteria. So the derivative is the rate of change. So keeping it general, we can write it like that. And then to specifically answer this question about when t equals 5, so f prime of 5 equals the rate of change. And again, this is going to be an average because it's from 0 to 5. Oh, I'm sorry. So the derivative is actually instantaneous. So, sorry, these are both instantaneous. So the rate of change is the instantaneous rate of change at 5 hours. So of that bacteria at exactly 5 hours. So it could have changed more or less before 5, but once it gets to 5, what it's changing right then at 5 hours is this derivative right here, f prime of 5. So for example, if f prime of 5 is, let's say, 3 bacterias per hour, that means at that moment of 5, it's changing about 3 bacteria. It's going to be, of course, much bigger. Bacteria are huge numbers, but it's going to be like about 3, right from 5 to 5.01 seconds or hours. So I actually don't love that example because 3 is not a reasonable number for bacteria. But I am going to talk a little bit about this rate of change, this sentence right here. This phrase, rate of change, that is the growth rate of the bacterial population in terms of this question at the time t.